Recording. Okay, so hello everybody. So today we have Quentin Paris, and Quentin is going to talk about online learning with exponential weights and metric spaces. I expect that it is his recent result on which is on archive. Yeah.
Yeah.
Okay, so please.
Thank you very much, Alexei. So I'm very happy to talk about this this work. So I have the outline of the talk is going to be pretty simple. I'm going to start by introducing some very basic concepts from online learning in the context of Euclidean spaces. And I will not suppose that anyone is particularly familiar with these concepts, so it might be it's going to be a very basic introduction, and I'm going to talk about in particular a specific online prediction algorithm, which is called the exponential weighted average forecaster, which is one of the most popular forecasting strategy in the Euclidean setting. And then I'm going to try to motivate a little bit the context, some different geometric contexts beyond the Euclidean space. And before we move to a fully geometric setting, I will do a small interlude where I would like to present the main ideas in 4 steps for the proof of the analysis of the algorithm of the EWA forecaster algorithm, to highlight the problems that we have actually in generalizing this to a non-Euclidean setting. And then I'll introduce the metric approach, which actually is a pretty straightforward generalization of the Euclidean one, given the notion of barycenters. And then we'll study an adaptation of the exponential weighted average forecaster that I call exponential weighted barycentric forecaster. And we'll try to talk about performance guarantees that we can give, in particular in connection to curvature bounds conditions. And then, so depending on time, I did not fill the slides for this part, but depending on the time we have, I might take the pencil to talk about this this interesting consequence. Okay, so let me start with a brief introduction. So of the classical online learning problem, or at least the way some formulation of the online learning problem. So it's very different from statistical learning in the sense that there is no probabilistic or statistical assumptions involved. It's a rather algorithmic process that that tries to be robust to adversarial environments. In particular, you do not suppose your data to be IID. So you just suppose that you have a given decision space, which in the classical setup is a convex subset of a Euclidean space. And you have a set of convex functions taking their argument in the decision space and taking real values. So this is the setup, and then you're facing the following repeated game in discrete time that you play in discrete time. So the player, or you can think of yourself as the learner or the player, you're asked to choose a point xt in the decision space. So you take a decision. After you've committed to your choice, the environment, say, okay, so the phenomenon you're interacting with reveals a loss LT in this set of loss functions. Then the player incurs loss LT of xt and moves on to the next round. Okay, so it's as simple as that, nothing special. So in this setup, there's several things that you might want to do, and the first thing that comes to mind is, try to minimize your cumulative loss at time n, or either you have a fixed horizon, or you're more ambitious and you want this to have a specific behavior as the time horizon n increases. But so this is a bit, I mean, there's no benchmark to compare yourself to. So, I mean, this is a bit there's no reason for this object to be small for any strategy. So a more reasonable approach is to try to compare yourself with a benchmark. And this is the point of the notion of regret. So the regret is this quantity. So there's many different possible ways to define regret. Or if you want this, this would be the analog in the context of statistical learning of the excess risk. So in this context, there's many ways to choose a benchmark, and the easiest here is to take this infimum, which is so I will actually comment it later on.
Sorry, I think there is a problem because the slides are fixed on the introduction. Is it intended to be so?
Seriously? You don't see the slides moving?
Yeah, me personally, I cannot see. I see repeated game for all T and stuff.
Wait. Okay, let me stop share for a second.
I'm not sure if it's on my side or your, but.
So what do you see here on the screen?
Wait one.
Do you see the slide number 3 called introduction?
No,
I see nothing.
I see black screen with a label Canton Paris has started screen sharing.
Okay.
Yeah, I think it's not on my side. No, it still doesn't work.
And now?
Now black screen.
Is this the case for everyone, or?
Yes, yes.
Yeah.
Okay. I don't know. I'm sharing a PDF, and I see. Okay, so stop share once again. So maybe I can try to share my desktop. So now you see my desktop?
No, we still are seeing black screen.
And now?
Oh yeah, now we're seeing the first slide.
Now we can see. Yeah, now we can see the slide.
Okay, I didn't do anything different. Okay, so I'm putting myself in full screen, and now you see it?
Yeah.
Okay. So should I go through the?
No,
so this is what
it was okay.
Okay. Okay. So this you saw this screen here?
Yeah. Yes.
Okay. So okay. So I was telling about this repeating game that we're trying to play, and I was describing the regret. So this you saw?
This we haven't seen, but now we see.
Okay. Okay. So okay, I was saying after that so once you hear, there's several ways to evaluate the performance of a player. That is, choosing in a repeated manner points in the decision space. So the first thing that comes to mind would be the cumulative loss. But so there's no way to know if there's, this could be very large for the best possible strategy. So a more constructive way to think about the problem is to compare yourself to a benchmark. So there are different possible benchmarks that you can compare your cumulative loss with. And the classical way to look at it is to look to take as a benchmark so this infimum, which represents the cumulative loss of the best fixed strategy in hindsight. So there's different possible benchmarks, or you can restrict your attention to strategies that do not move too much. but basically this is the simplest, so I'm going to stick to this notion. And we add usually, because we want to make a type of worst case analysis, we add a supremum over all possible losses that the environment can give us along the way. And so this is what I said, this is the cumulative loss of the best fixed decision in hindsight. So this is what I mean, a bound on the regret is a form of performance guarantee. So, and typically you see that non-trivial bounds would be bounds which are sublinear in n, like typically square root of n or log n, as we'll see. Because you see that obviously if you play a game with bounded losses, having a regret of order n is trivial. So non-trivial bounds that actually show that you're learning something are bounds that are sublinear, for which r n divided by n tends to 0. Okay, so just a small remark to compare this online learning setup to convex optimization. So maybe I didn't insist enough, but the losses in the class capital L, or that we consider, are usually supposed at least convex. So you see that very well that given one loss, fixed loss in the family of losses, straightforward application of Jensen's inequality tells you that the suboptimality gap, the average of your points of your decisions is bounded by the regret divided by n. So this is possibly a suboptimal bound as far as convex optimization is concerned. But this shows that essentially obtaining a bound on the regret for the game is something that guarantees, that provides you guarantees for the optimization of a fixed function in your loss class. So this is sometimes why this online learning setup that I've described is called online convex optimization. If you want, it's like if you were doing convex optimization where the function, where the objective function is changing at each step. Okay, so this was just a comment. So now let me describe, come to the so-called exponentially weighted average forecaster, which is, I think, if I asked you to come up with a strategy for solving this problem, or for trying to minimize the regret, some of you at least would probably think of that. So suppose, the setup, I'm still considering the classical Euclidean setup, where the decision space is a convex subset of Rd. And now I'm going to fix a prior distribution over the decision space that you can think of that you can suppose M to be a compact and convex set over Rd with non-empty interior, and you can think of M as being the uniform distribution over M. And then what you do is your decision, you take it to be the average of a certain distribution MT, where MT is something that you update along the way. So at time 1, it's your prior, okay? And at time t+1, you simply reweight your previous distribution by exponential minus beta t+1. So beta t+1 is simply a positive tuning parameter times the loss LT. So the structure of this update is pretty natural in the sense that, so if you look at the structure, so it promotes decisions with a small cumulative loss. Okay, so if you at a given time, so in the game we're playing, this is something I should say. When the environment reveals the loss LT, it reveals it as a function. So in particular, I have access to the whole function, and not simply at the point xt. So in which case the problem would be more complicated and would be known as a bandit problem. So here I'm in the full information setting where when the environment reveals the loss LT, I have access to the whole function LT. And in particular, I know which point would have been good or better, which have been worse or better, and I can reweight my measure MT+1 as such. And in particular, the exponential I mean, the exponential form of the weights simplifies a lot the update and the analysis, as we'll see. So if the algorithm is clear and if it makes sense, we can move on. Otherwise, I'm happy to answer questions if the algorithm doesn't make a lot of sense. Okay, so let's move on. So this has been studied under many possible assumptions, and I'm going to give you one example of analysis that we can make of the algorithm by supposing the losses to be xconcave, and I'm going to describe this. So for us, xconcavity is simply a name I'm going to give to a certain property, which is by definition that L, a loss, is called beta x concave if exponential of minus beta L is concave. Okay, so it's a little bit more than convexity. So in particular, you have this this sequence of implications where you can see that strong convexity with the Lipschitzness, implies x concavity, and x concavity implies convexity. So in a sense, you know, except for this Lipschitz requirement, I like to think of x concavity of like something between convexity and strong convexity. And the typical example, of course, is so minus log is probably the best example of a 1x concave function. So it's a bit more, but so you see clearly that it's not strongly convex, but according to the definition, it's 1x concave. Okay. And so under this assumption on the loss, there's this very interesting result that was provided first by Hassan, Agarwal, and Kale that says the following. So if you suppose that M is a convex body, so meaning a compact convex set with non-empty interior, and if you take M, if your prior is the uniform distribution on M, which I mean, if you're starting the game with no information, makes sense. And if every loss in the loss class or the class of loss functions is beta x concave for a given beta, then for all possible time horizon, if you run the exponential weighted average forecaster with this tuning parameter equal to this x concavity parameter, then you obtain a regret, which is upper bounded by d, the dimension of the convex set, times log of n. So that's a pretty nice result. It's clearly non-trivial because it's clearly sublinear. And it's pretty much the benchmark. I mean, it's known that up to constants, you cannot hope to do better than that. And okay, so this was the point, this is the starting point of my work, where I tried to understand how much can we depart from the setup, which is on the screen here, and in particular, if your set M is not a subset of a convex, is not a convex body in RD, but something with a bit different. Yeah, and something that's quite interesting with this result, if you think about it, it's that it requires rather little assumptions. So again, so there's something quite nice in this result is that you do not require Lipschitzness of the losses, which in some cases is, I mean, as is often required in learning scenarios, and usually comes at the price of assuming that everything is bounded. So here we need boundedness of M because because of the prior we're considering, but a priori there's no reason to suppose the boundedness of the decision space if you take a different prior. Okay, so just a few.
Ask?
Of course, yeah.
And for example, if you consider unbounded M and loss function, just quadratic functions, that it doesn't fall to your setting, yes?
So if you consider, so actually, if you consider unbounded, so there's several setups. So unbounded M and simply convex losses, you might guarantee. I think you can show that. I'm not sure about the rate exactly, but I'm sure that if you take the beta t's to be of order 1/√t, in this case, you can show that the regret divided by n tends to 0.
It's quadratic loss.
Yeah, with quadratic loss, with the convex loss, or actually with the strongly convex loss. With a strongly convex loss, you, I think you still need a boundedness of the gradients. So this goes a bit. This seems to ask boundedness of M.
But not just Lipschitzness of gradients of L. Maybe it's enough or not.
Not just boundedness of I can guarantee that if you're with a if you have a strongly convex loss with with bounded gradients, so this I mean this supposes the decision space to be bounded. This you can have a logarithmic regret as well.
Okay, so
yeah.
So it's unbounded case. It's not so clear.
Unbounded case. So it's maybe easy, but I don't have the result in mind, and it might be easy to obtain something suboptimal, but I don't have optimal results in mind.
Okay.
Yeah.
Thanks.
Okay, so it's pretty easy to convince ourselves that so this is a nice prediction strategy, but it's not very well suited for non-Euclidean scenarios. So suppose you were playing this game on the surface of a sphere. You see very well that the averaging procedure that we're implementing takes us out of the sphere at every step if we were to do this. So that's not very consistent with the geometry of the problem in this case. And actually, the observation is the same for any submanifold of RD. If you just average according to the natural notion of, I mean, if you use the Euclidean structure for defining your averages, you're not going to do a good job. Okay, so the end game, the end we have in mind is applying our result to the case of the Wasserstein space, where the points that you're actually trying to, the XTs, what I'm calling XT at every step, would be a probability measure. We equip this probability space with the Wasserstein metric. So I'm not totally there in terms of results. There's I mean, except from some particular cases, but the result provides a first step in this direction. So now, before we try to address the case of a geometric, fully geometric setup, I want to do a small look. I want to have a small look, actually pretty detailed, but quite systematic look at the proof for the Euclidean setting. So this systematic description of the proof is not necessarily the one you find in the literature, but it's the one I had to do to kind of understand what works and what doesn't in a non-Euclidean space. So the first idea on which the proof relies is Jensen's inequality, which is rather simple. And I'm going to walk you through the first step. So by assumption, every loss that the environment is spitting out is beta x concave. So this means that the function exponential minus beta lt is concave. And therefore, by definition of my decision xt is precisely the average of the measure mt. I have this first inequality, which after taking the log, I clearly obtain a bound on the loss at a given time by this log of an integral of an exponential, blah, blah, blah. And if I sum this, I obtain a first possible upper bound or control of my sorry cumulative loss, that is the first step. Okay, so the first step is Jensen's inequality. The second step is what I call exponential magic, because it's I don't know how to actually describe this, but the very specific structure of the weight updates, or the update of the measure mt, and the properties of the exponential allow me to transform this this sum of log of integrals, and basically bringing the sum into the integral. Okay, so we don't need to necessarily prove this in detail, but it's a rather straightforward step that is really related to the specific choice of the weight update and the exponential function. So combining this with step one, we have a new upper bound on our cumulative loss that now has a slightly more friendly, slightly friendlier shape, in the sense that it's not anymore a sum of logs, but it's a log of an integral of an exponential. Okay. The third step is really interesting. It's the one I find the most interesting, is the application of the Gibbs variational principle that states in full generality the following. Okay, so whenever the integrals make sense, it's basically gives you a description of the Legendre transform of the relative entropy. So it says that the left-hand side, which is precisely the object that we have after step two, can be written as the infimum of a simple integral plus a relative entropy term. Okay, so where relative entropy is the Kullback-Leibler divergence between mu and m, as is. And so you see that coming back to step two, just to show you that this is exactly the expression we have to bound. So in the slide after that, so the expression I gave was for f equals to this sum. So if we apply the Gibbs variational principle to the step two, now we obtain this, which now is great, because on the right-hand side, if you look carefully now, there's nothing that depends on our strategy now, okay, except the choice of our prior, basically, because all the rest on the right-hand side in this infimum involves the losses which are given to you by the environment. Okay, so that might be influenced by your strategy, but it's not directly connected to xt. And the entropy term is involved only the prior that you chose. So in a sense, now if you want to have something a bit more explicit, you might want to choose a specific mu, okay, to upper bound this this infimum by something more explicit. And this is when we use, I mean, in the classical proof, we use the properties of the Lebesgue measure. So precisely one of the properties that is useful in our case is that, so if you take x star, so actually think of x star as being anything. Sorry for this, it's a typo here. This is in the proof, this is what we have to consider, x star, which is a minimizer of the cumulative loss. But for the sake of this slide, take x star to be anything. So you take x star to be any point. If I fix epsilon, and I look at m epsilon, which is so remember m is our convex decision space, and what I do is I contract all my convex set towards x star by a factor of epsilon. Okay, so this is in effect what I'm doing, and what's happening in terms of the measure of m with respect to the measure of m epsilon. So this is what we look in this next slide. So sorry, this slide is a bit heavy, but I'm going to walk you through it. So on the top of the slide, I've simply reproduced the drawing. So x star is a point in my convex set, and m epsilon is the set I obtain when I contract everyone towards x star by a factor of epsilon. And so in the context where m is the uniform measure on the convex set, what I can do is I can look at the image of this uniform measure by this contraction, essentially. So now I'm just considering the uniform measure on m epsilon. And it's easy to compute that the relative entropy between m epsilon and m is actually d time log of 1 over epsilon. And this comes, I mean, the most important part here was to observe that if m is the Lebesgue measure rescaled, okay, on the set m, then m of m epsilon is just epsilon to the power d. And this is something very specific to the Lebesgue measure. And this is the heart of the proof at this point. Okay, so I don't give you the end of the proof because it's not the idea is there. You got all the ideas of the proof. Now you have to tweak a little bit the last formula where you see that we upper bound the infimum by choosing a specific mu, which is m epsilon. And then you use the assumptions of x concavity. You choose a right epsilon at the end of the day to minimize this expression, and you arrive to the result. So this was simply to actually outline the 4 important parts of the proof and to show what can be easily generalized to the non-Euclidean setup and what doesn't. So Jensen's inequality is clearly depending on the Euclidean setting. So it does depend on the Euclidean setup. And so this is an issue. We have to think of something or generalize this result. So the exponential magic, so I won't ask you to see this straight away, but actually it's absolutely not connected to the Euclidean structure of the underlying decision space. So it goes without a problem, and it's not connected to Euclidean setup. So this can go in much more general settings. And same for the Gibbs variational principle. This works very well in a more abstract setup. There's no problem. But finally, the last thing, this specific property of the Lebesgue measure now is very connected to the Euclidean geometry. So to sum up, there are 2 challenges to try to move from the Euclidean setup is to see how to compensate for the lack of Jensen's inequality and the lack of the Lebesgue measure or equivalence. So before explaining how to deal with these results, let me simply show how to intuitively generalize the algorithm, at least from a theoretical point of view. So we're dealing with averages in the exponential weighted averaging algorithm. So it's natural to think of employing barycenters instead of averages. So in this setting, I'm just going to consider the decision space to be a metric space. So M equipped with the metric D. M, small m, which plays the role of my prior, I'm going to take it as a measure that has a second moment. Okay, so a probability distribution on my set M, such that this integral is finite for every fixed x. And the natural notion of average in this setup is the barycenter, which, of course, the expression now on the left-hand side does not make any sense. If I am in a space with no Euclidean or linear structure, I cannot define this integral. However, I can define B as a minimizer of this functional on the right-hand side. And actually, it happens that these 2 definitions match totally whenever the underlying space is the Euclidean space. And the measure has a second moment. Okay, so now you see that given this new definition of average, the definition or the adaptation of the algorithm in this setup is pretty straightforward. So what I call the exponentially weighted barycentric forecaster is simply goes as follows. So I fix a prior over my metric space M, and I define xt at every time step as a barycenter of MT, meaning a minimizer of this functional here, where actually MT is exactly as before. So this update is actually not dependent on the Euclidean structure. It makes total sense to decrease the weight of points in my space given the losses they've produced. So this weight update still makes sense. It's simply the averaging procedure which is adapted. Okay. So now to study the performance of this guy. So just as a disclaimer, in this talk, I will not talk about computational matters, which are very important. But you see that in the previous, so here we're replacing the computation of an average in the Euclidean setup, the computation of an integral by this optimization problem, which is potentially, you know, depending on the structure of the metric space you're considering, might be a huge challenge in its own. But I'm going to avoid this discussion in today's talk and simply look at the theoretical properties of this guy. So let me remind you that in this setup there are two challenges: the Jensens inequality that, you know, we might want to establish for barycenters, and this notion of measure contraction property that was used for the Lebesgue measure in the Euclidean setup. So actually, I thought this Jensens inequality would be maybe the I thought it would be either impossible to solve or found in the literature, but in the setting I was looking for, I did not find it in the literature. So it took me almost a year to try and figure this out, and actually works in a relatively large setup. And it turns out that if your metric space is geodesic, because remember, we need, I mean, for Jensens inequality to make sense, we want to have a, we want to apply to convex functions. So we need a suitable notion of convexity. And therefore we want to, for instance, one notion is convexity along geodesics. So I require the decision space to be geodesic. So if my space is geodesic and with a lower bounded curvature, so in the sense of Alexandrov, and I'm not going to define this. I'm not going to define this today precisely, but think of the sphere as something that is lower, has a lower curvature bound by 0, or actually by something positive. But so I'm gonna just state that as it is, and it's not really important what k is, as you see that it does not appear in the result. So some lower bound on the curvature is enough. And it turns out that for any convex, geodesically convex function, and any measure m on P2 in P2 of m, meaning a probability measure with a finite second moment, if it has a barycenter, then what we would expect for Jensens inequality actually holds, meaning that f of x star is going to be smaller than the integral of f, or the average of f with respect to m. So that's the first challenge that, in a sense, is okay, actually works. And the second, before discussing the second problem of measure contraction, I just want to have another look at the case of the Lebesgue measure. So what the measure contraction property that we've used so far, what it's actually saying is the following. It's saying that if I fix a point x0 in RD, any point, and I take any set A, measurable set which needs not contain x0, and if I look at the set A epsilon, which I obtain as follows, so I take every point x in A, and I contract it towards x0, by a factor of epsilon, according to this formula. So if I do this for every x in A, I obtain a set which is A epsilon, okay? And what happens is that the Lebesgue measure of A epsilon is simply epsilon to power d Lebesgue measure of A, okay? So if we look at this carefully, this is actually a property of a triplet. It shows something on the interaction between RD as a vector space, the norm, the Euclidean norm, because actually it's, or if you want, the Euclidean structure that tells you that the shortest path between x and x0 is this straight line, okay, and the Lebesgue measure. So it's actually a characteristic, one could say, of the metric measure space, which is a triplet, okay? And this is what we're going to try to do, is to look at a systematic notion of how measures in a metric measure space behave when we contract sets towards points. And this actually happens to be very well studied in the literature in the context of people looking for notions of a synthetic lower curvature bound in the sense of Ricci. So I'm going to give you now a very a very technical, no, in the slide afterwards, sorry. So before I arrive to this abstract definition, just to tell you that we might want to do the same thing in an abstract setup. So if I give you a triplet MDM, where MD is a geodesic space and M is a reference measure on M, I can do the same thing, but instead of looking at straight lines, I can look at geodesics, shortest path between 2 points. So for every point X, I can look at the geodesics from X0 to X and look at gamma epsilon, which is the value of this geodesic at time epsilon. And when I do this for every X, I form a set A epsilon, and I call this the contraction of A towards X0 at time epsilon. So in words, this is the description of this set. So the set of gamma epsilons, where gamma is a constant speed geodesic from X0 to a point in A. Okay. So this is how I define the contraction of sets towards points. And now I'm going to give a big definition, which is unreadable. Let me parse the statement with you. I fix a kappa in R, which plays the role of a lower bound on curvature. P strictly positive, strictly bigger than 1, that plays the role of a dimension. And we declare that the triplet MDM, so this is a metric measure space. It's a space with a metric or distance function and a measure. Satisfies the MCP kappa P property. So MCP stands for measure contraction property. If the following lower bound holds on the measure M, so M is my reference measure, and A epsilon X is this contraction of the set A. So I'm not expecting you to read this carefully. Okay, so it's a nightmare to figure out what this is, but actually it involves very natural trigonometric functions for those of you who know geometry. And instead of looking at this definition very carefully, what I'm going to do is simply give you the intuition of what it means. So the main intuition is that this measure contraction property is a synthetic Ricci curvature lower bound. And to show you why, for instance, there's a result of Ota in 2007 that gives a very nice equivalence in the following setup. So if M is a complete Riemannian manifold of dimension P, if you take for D the Riemannian distance and M the volume measure, okay, so what would be, if you want in a sense, the Lebesgue measure in RD, this would be the volume measure in your manifold. Then it's equivalent to require the Ricci curvature of M to be lower bounded by kappa and to require MDM to satisfy this MCP kappa P property. So this really shows that in the context of Riemannian manifolds, this horrible definition I gave before is essentially requiring a lower bound on a Ricci curvature, which is something also I would not go in detail, but so either, but basically it's telling you it's a lower bound on curvature. Okay. So now we're in position to state the result, and you see that we're not far. I mean, given the outline I gave for the proof in the Euclidean setting, and the fact that we have an analog of Jensens inequality and of this measure contraction property, I can safely, state the results without being too much of a surprise. So the result is the following. So if you suppose your decision space to be geodesic with a lower bound on the Alexandrov curvature by something which is in R, and if your metric and if you choose a prior M such that the metric measure space MDM satisfies this MCP kappa P property for positive kappa. So I'm going to state two results, and this one is with positive kappa. So essentially a positive lower bound on the Ricci curvature if you want. So this, of course, these two notions of curvature interact, but I won't spend too much time on that. And if, so I didn't talk about this, but this is the quite straightforward analog of what happens in the Euclidean space. If I suppose all my losses L in the loss class to be beta x concave along geodesics, then I obtain this upper bound on the regret, which is exactly the same as for the Euclidean setup with uniform measure. So the first remarks that come to mind is that, so first of all, we recovered the results of Hazan and Al in the sense that, I mean, they cover the same, our assumptions cover this case, okay? And but it's compatible with many more setups where, for instance, it's compatible with Riemannian manifolds of dimension P and with a lower bound on the sectional and Ricci curvature. And it's also compatible with the two Wasserstein space. So there's a little so for instance, I could provide statements for specific choices of loss functions and the space of Gaussians, but to go beyond these kind of simple examples, I still have some things to figure out, so I didn't want to spend too much time on the Wasserstein space. But now, what happens in the case of so kappa, this curvature parameter that appears in our assumption? What if we suppose it to be negative? So we also have a result in this case which is a bit less clean, but almost as clean. So in this setup, so we have almost the same assumptions, except that now I'm supposing this curvature parameter to be negative. So it's a lower bound on the Ricci curvature, but it's possibly negative. Then I have to assume, so apart from these three assumptions that were present, in this case, we have to assume some integrability condition on our prior that takes this form. So it's a bit, I'm going to try to parse you through it, where phi, this function psi, this function psi is a bit, it's not super friendly, but actually if you plot it, you see that it behaves rather well. So it's a nicely behaved function, this function psi around both 0 and plus infinity, basically. It's a bounded function that goes to 0 at infinity. So what we're requiring actually is that this integral, which is here in red, is strictly positive. That basically is telling you that M does not put too much weight on points at the, actually, yeah, so essentially it's so one way to look at this is to see that if M is a bounded set, okay, you could and if you plug here the diameter, if you plug the diameter, you would get something finite and strictly positive, and therefore this would obviously be the case, satisfied if M is a bounded geodesic space. Okay, so apart from the interpretation of this requirement, what we have in this case is up to a constant, the same upper bound. We just have, in addition to the previous result, this log term, which is a constant, so it doesn't really matter. And that's it. Essentially, this is all. I think I'm actually I'm in time.
Okay, thank you very much. So, dear colleagues, what questions?
I have a simple question concerning Wasserstein space, of course. You said that once you have geodesically convex functional, then it is barycentrically convex. Yes.
So yeah, the Jensens inequality is true. Yeah. So here I gave a simplified version of the result. You need, in addition, your function f to be locally Lipschitz around x star. But yes.
No, usually in Wasserstein setting, like it is known that if functional is generalized geodesically convex, and we have barycentric convexity.
Okay.
Yeah, but I mean, I didn't see.
So actually, in the context of Wasserstein space over a manifold,
yeah.
So which is both more general and less general than my case, because so it's there's the paper by Kim and Pass, who it's called Wasserstein over manifold.
Wasserstein barycenters over manifold.
Exactly. So this paper, they have a section on Jensen's inequality, and they actually prove Jensen's inequality for most geodesically convex functionals, like the three classical ones.
Yeah, but they are also generalized geodesically convex.
Okay. Okay.
So I mean, here there are still some additional assumptions on regularity of F.
In the case of Kim and Pass?
No, I mean, in this theorem, if we are talking about some infinite dimensional space, something like this.
Yeah, so the only assumptions I'm considering is geodesically convex and locally Lipschitz around X star.
Okay. Yeah. See.
The paper for Jensen is a different paper, and it's on arXiv also, so you can have a look. And
okay,
yes.
Thanks.
Yeah.
Any other questions?
Yeah, and another question. Yeah, it seems that in this problem we can define any kind of barycenter related to the class of loss functions that we have, like maybe something, I don't know, something like in Vovk aggregation algorithm.
Yeah. So this essentially what you need is yeah, I see what you mean. So this question of, I think, so-called mixability. So
yeah.
Vov calls this mixability, which is essentially asking for this inequality to hold. So the one which is, do you see my yeah. So and in particular, instead of 1 over beta, you could have a constant divided by beta. You could still have a regret bound. So this is what, actually it's kind of cheating. It's like you're asking for you see from the proof what you need, and you ask this, you require this as, yeah. So in principle, you can ask less than Jensen's inequality. You can ask for mixability, which is that this inequality up to constant holds here.
Yeah, but you still need this, so some even more complicated measure contraction property in this case. Yes, like a measure contraction property with respect to this mixing, something like this.
Maybe.
Okay.
But I didn't look in this direction. Yeah. But actually, what I showed, there's so the version on arXiv of this paper has a small paragraph on Wasserstein where I show, in a sense, that the Wasserstein distance squared is mixable. So it's clearly not, it doesn't satisfy Jensen, but precisely we have exactly this inequality with the constant here.
Mm-hmm.
So
Okay.
this is something that I think is worthwhile. But yeah, so the classical setup of applications of application in the Wasserstein space would be when your loss. So you play. Your losses are called back are the relative entropy. So LT is a relative entropy with respect to a log concave measure. In this case, this provides you and this I didn't talk about online to batch conversion, but this would be an application. This you could apply this result for generative models or stuff like that. I guess.
Okay.
But yeah.
Okay. Any other? Looks not super easy.
Well, it's just a copy of the Euclidean proof with a few. But the algorithm is, I mean, there's still a huge problem, which is computation of this algorithm in practice. And I believe this is interesting. I mean, for students, for example, this would be really interesting. Because and also you can think of a sampling strategy where you, instead of computing exactly the barycenter, you sample according to the distribution, and then you have bounds on the expected regret. And this is a interesting thing to look at, I believe. So instead of computing exactly the argmin here, you just sample according to MT at every step. You sample a random variable, capital XT, according to MT, where MT is given by that. So essentially, you're sampling. If you're, so you see that if you're starting, if your prior M is, you see that what's happening here in RD, for instance, if you take for M a uniform measure, then you're sampling according to log concave distributions, because you're taking exponential minus convex function. So I think it's within reach of standard algorithms. And I think this is something interesting to look at.
Because in exp3 and exp4 algorithms, as I remember, they use sampling, not computing of some average value. So in bandit setting. Yeah,
so actually this is exp3. So all this is it doesn't work if I don't have access to the whole loss function LT. In this case, actually, I didn't try to adapt bandit algorithms in this setting, but my guess is that it's going to work the same way, because what you're averaging is really the values of the loss, and these are real numbers, and not the averaging procedure doesn't happen in the decision space. So I think this would work.
Yeah, for me once it was interesting to consider such a case, but the main problem was that I haven't found a suitable update rule for MT in the setting where you have, say, even some continuous structure like a manifold, and you get only one number, which is loss of decision you've taken, and I do not know how to do an update.
Yeah, that's a.
It's a big question, and it is not answered in the literature still.
Yep.
Because all things they can do is zooming algorithm and Lipschitz bandits, but it's a bit different story. So they use discretization, but it seems to me that the analysis of online learning may give some ideas how to proceed in bandit setting, but the main problem is the update rule. I just don't know how to do it.
Yeah, it looks like an interesting problem.
Okay. Okay, Quentin, thank you very much.
Thanks.
We can talk.
See
Thank
you
you.
guys.
Yeah, so thank you.